Welcome everybody. Feel free to get food as you go and so on. Welcome to another IDE seminar. It's great to have everybody here, and it's particularly good to have Jessica Hullman here, the Ginny Romadini Professor of Computer Science at Northwestern. She's been working on developing theoretical frameworks and tools to transform how people combine their knowledge with statistical models. She's working on human-AI complementarity. She's working on AI and AI agents for behavioral science and lots of other cool stuff. And we're really happy to have her. So please welcome Jessica. Thanks.
Thank you for having me. So I'm going to talk about the value of information in AI or model-assisted decision-making. And the work I'll present is in collaboration with several others. So my PhD student, Ziang Guo, has I think he led most of these projects. Yifan Wu, who's also here, is author on many of them, as well as Jason Hartline, my colleague at Northwestern, and Burke Austin on one of these. So back in 1954, Paul Meehl wrote about this perplexing but very robust empirical result that was observed by decision scientists, which is that in many contexts where we expect human experts to have some useful domain knowledge, when we compare their prediction to predictions from a statistical model trained on some historical data, the statistical model will generally outperform or match the accuracy of the human. In other words, statistical prediction tends to outperform clinical prediction. And this is a robust result that we continue to see in these types of comparisons that continues to bother us, I think, because we assume generally that humans do have useful insight to offer over what we could possibly encode in a statistical model. So the human doctor might be able to interact with patients or observe features that we're going to have trouble encoding, for instance. And so today we continue now, or what we do most often is try to pair humans with AI models. So we're not willing to give up on human expertise, and so we think we can get the best of both worlds. And the goal in doing so is usually what we call complementary performance. So we hope to see that the performance of the human assisted by the AI is better than the performance of the human alone or the AI alone. In practice, however, in the last decade or so, there have been a number of empirical studies of humans in different domains using AI as decision support. We often find that we don't see complementary performance. Generally, when the AI outperforms the human in isolation, we tend to see that the human with the AI underperforms the AI alone. This has been seen in a variety of domains: medical treatment selection, various financial decisions. And so these empirical results then motivate this sort of breathless rush to try to fix the problem by doing things like designing a better interface or designing new explanation techniques to help the human calibrate trust. Many times these techniques do not fully fill the gap. We still see humans sort of underperforming the AI alone. And so we're left trying to figure out, what's going wrong and how can we improve things. And I think part of the problem that prevents us from knowing how to improve human AI decision-making is that we lack a clear theoretical foundation for answering many basic questions that might come up when we deploy AI as decision support. So things like, in this context, is there even potential for complementarity? Is the human over or under relying perhaps on the AI? What makes a good explanation for this particular decision problem? And how does the AI versus the human's information access and use compare? So we struggle to answer these sort of basic questions, and what I hope to convince you of today is that part of why we struggle is that we have unclear measurement targets. And so what I want to hopefully convince you of is that if we can have or find more principled ways to measure the value of information to some decision problem where a human is using an AI, we can make a lot more progress. And the value of information might mean the value of information in available features that describe a decision instance. It might be predictions. It might be explanations of those predictions. It might also be things like agent decisions, whether human or an AI. So our approach will be based in Bayesian decision theory. We're going to assume a decision problem in which we have some decision maker, and they are going to observe some signal, some features of the decision instance. Their job is to choose an action from some action space A, And at the time of the decision that they make, there is some state of the world on which the quality of their decision depends, but it will be uncertain when they make the decision. So eventually nature will endow some ground truth state Y, and we can think about the quality of the decision that the agent made in terms of some utility function, which takes an action and a realized state and provides some real valued score. Often we'll want to think about what is the expected payoff or expected utility of an action, and so we can think about calculating this expectation given some belief distribution P that describes our beliefs about the probability of the state. The final component of a decision problem is going to be what we call the information structure, the joint distribution over the ground truth signals Y and the ground truth state Y and the signals X. And so essentially, we could also call this the data generating model. Whenever we want to evaluate decision performance of some agent, we're going to have to do so with respect to this information structure or model. So let's just take a simple example of a decision problem to make this more concrete. Imagine that ultimately what I care about in making my decision is whether it rains or not. And the choice I'm trying to make is, should I bring my umbrella? So the signal or the forecast I'm going to use is going to be the most rudimentary type. I could go outside, I could see, are there clouds in the sky? And the joint distribution, this information structure, might look something like this, where half the time there are clouds, the other half of the time, half the time there's no clouds, half the time there are clouds, and the half the time when there are clouds, 50% of those times it rains. My utility function might look something like this, where I get the most utility out of not taking my umbrella when it doesn't rain. I do worst when I forget the umbrella or leave it at home and then it rains. And we can even sort of show a graphical representation of this simple decision problem. So here on the x-axis, we have the belief about the state, whether it rains or not. And on the y-axis, we have the expected score. And so then we can look at our two actions and plot the expected score of that action over different beliefs about the state. So we get something like this for each of our two actions. All right, so this is our decision problem specification. What we're going to want to do in order to define the value of different signals to a decision problem is think about how do we solve the decision problem in an optimal way. So how do we define the optimal decision on any given instance? And here we're going to make use of this notion of a Bayesian decision maker who's going to maximize their utility. So they're going to arrive at the optimal posterior beliefs on any given instance, and then they're going to choose the utility maximizing action. And so, what this looks like is that our Bayesian, we're going to assume they have oracle access to this information structure, this joint distribution over signals and state. So they're going to start with the prior defined by the information structure, the prior probability of the state. What's the probability it's going to rain? On any given instance, they're going to observe that instance, and then they're going to update, like a Bayesian, to posterior beliefs, where, again, they have access to the information structure. So they don't know the ground truth, but they know this joint probability distribution, and that allows them to update. The tildes here just mean random draws from a distribution. And then finally, they choose the utility maximizing action under the Bayesian posterior belief. So we're using PY for the prior and QXY for the posterior, given some signal X. And this AOPT is our utility maximizing action under some beliefs. Okay, and so looking at the graphical representation here, we can now see where the prior beliefs are. And we can look at how these two lines indicating actions, where they intersect, a given belief point on the x-axis. And so we see under the prior, my optimal action would be to not take my umbrella. However, if I observe clouds, my posterior then tells me that taking my umbrella is the utility maximizing action. Okay, so this gives us sort of how do we, define the optimal decision on any given instance that we observe. What we're going to want to do in order to assess performance of AI-assisted humans is to be able to talk about benchmarks over this decision problem as a whole, so over the information structure as a whole. And so, what this is going to look like is calculating first a benchmark representing the best attainable performance on that decision problem, which is equivalent to the expected performance of the rational agent who is going to optimize using the signal. And what we can do to sort of quantify the value of a given signal to the decision problem is compare this benchmark to a baseline, which is going to represent the expected score of the rational agent if we only give them access to the prior. So if they only know the prior probability of the state, say, the prior probability it's going to rain, then they're going to have to choose the best fixed action under that prior. And so we're essentially measuring what is the boost in performance in the best case when we offer the signal. So we'll call this the value of information. And this general sort of calculation is what we'll see in the various applications I'm going to talk about in the rest of the talk. What we can do once we sort of theoretically quantify the value of information to some decision problem is then observe the human using that signal, whether it's a signal involving an AI prediction or some other information, and we can see where they fall relative to this sort of best dumb strategy and sort of best attainable performance. Okay, so today I'm going to use this decision theoretic framework and this notion of quantifying value of information to answer a few questions that come up commonly when we're talking about AI as decision support for humans, including, how do we know whether a human has relied on an AI at an appropriate rate? How do we know if we have a good explanation for some decision problem of the AI prediction? And how do we tell how agents are using information and how we might be able to improve that? All right, so let's start with measuring reliance and complementarity. These two, as we'll see, will go together. So as I mentioned, many of these empirical studies that have compared humans with an AI to AI alone performance and human performance find that the human with the AI underperforms the AI alone. But one question that often goes unanswered when we get these sort of results is, well, how bad is this, relative to what we might have seen? Could we have expected much complementarity here or not? And similarly, even when we see the human with the AI outperforming the better of the two in isolation, we still don't know how good it is. So, are they achieving sort of nearly the best attainable performance we could hope for, given the information in these AI predictions and these human judgments, or is there still sort of a lot of improvement to be gained? And if we look at the literature on appropriate reliance or over and under reliance on an AI, what we find is that a lot of times the measures that people are using to define, good reliance are based on post hoc measures of accuracy. So, for example, researchers will assert that the human should agree with the AI when it's right and disagree when it's wrong. And the problem with this kind of target when we're studying reliance is that we're not accounting for what information was actually available at the time of the
So I'm wondering, are you only looking at the information that's available to human, or is resistance that is resistance of humans to AI recommendation, is this part of your informational structure that's want to overcome? Because sometimes not taking AI's advice is a resistance that maybe less than or different.
Yeah, we're not going to try to distinguish resistance necessarily from under reliance, but we want a clear sort of target for measuring reliance and versus observed reliance versus optimal reliance. So we're not going to distinguish between resistance versus under relying for other reasons.
So actual adoption for whatever reason.
Yeah. We will try to distinguish sources of loss, which is what I'll say now. So our goal is going to be, in this context where we have a human with AI decision support, to first define what is the best attainable performance on this decision problem, given some particular human or set of humans and some particular AI model. And then we can look at the expected performance of the better of the two agents in isolation, and this will give us a way of defining what we'll call the value of complementation. So this is sort of the max boost we could expect going from the better of the two agents in isolation to having the combination of their judgments. We can then, actually observe our human with the AI, and we can, see what the loss in performance is relative to the best attainable performance. And we can even go a little bit further and try to distinguish different sources of that loss. So maybe they relied overall too much or too little, or maybe they were simply unsure of when exactly it was in their best interest to rely, even if they sort of, the rate of reliance was okay. Okay.
Sorry, but when you say that, so if they were relying optimally on AI signal, we would get to this optimal performance, but then it would mean that AI by itself would get us to this optimal performance.
No,
I'm
so
just trying to
AI by
picture what
itself
the-
is going to be this green. So this is what we expect, how we expect the AI to do if we're randomly drawing from this distribution.
I understand the picture, but then what does it mean that we are not relying enough on AI and it's causing us loss of performance?
So we're going to look at the observed human reliance with the AI relative to the optimal reliance. But this x-axis here is the expected score on the decision task. So, we're not just looking at the difference in rate, but we're looking at like our ultimate outcome that we care about is the difference in score. And so some of that can come from simply not relying at the right rate, but some of it can come from not relying in the instances where it is in your best interest in terms of the difference in expected score from the AI versus the human.
The AI can be wrong, and the human is best when it knows when it's right and wrong, and optimally chooses given the information.
It's not just
If I can
right.
follow up on that, there happens to be a huge literature on expert advice and the value of expert advice and when it's followed, when it's not. And I'd just like to know, to what extent does that literature inform this one? Because I could magically hide AI and say the world's greatest person, the typical doctor, et cetera. So just.
Yeah, I mean, what we want to do is assume we have two different sort of agents making predictions that are going to then inform some decision task.
Right.
And so it could be multiple humans. It doesn't have
So
to
it
be.
transcends it. You're purely a value of
Yeah, I'm gonna
information
talk
play
about-
in a microeconomic sense.
Yes, right. Most of what I'll present, I'm specifically gonna apply it to cases where we have human and AI, but most of it applies, I'll tell you if I'm making assumptions about humans versus AI, intelligence.
Only other thing that I would ask about in this regard, particularly because you're from the Chicago area here, is any behavioral economic aspect of this, because complementarity can indeed be influenced and informed by, quote, cognitive, or let's just say agentic biases here.
I'm not gonna go too much into those. Most of what I'm gonna take is sort of statistical perspective. What can we say just treating these as inputs to some decision problem?
Great.
All right, so that's our goal, to do all this. Let me talk about how we get there. So we're gonna assume a common class of workflow for AI decision support that is often assumed in the literature, which is that we have some human expert, they observe some instance characterized by some features X. We assume that they can come to their own independent prediction about the state, YH here we'll call that. And we assume that they also have access to some AI prediction distinct from their own independent prediction. And then typically it is the same human decision maker that made this prediction that then chooses whether to go with their prediction or this AI prediction on any given instance. So we have a prediction problem here and we also have a decision problem. What we want to do is figure out what is the best attainable performance on this decision problem. So we want to separate that out.
Maybe I missed this, but are you assuming that X is equally presented to both human and AI, or can different X's go into humans and AI?
Different X's could go in.
Okay.
So yeah, there will be an X. I'm not going to distinguish them, but I think the results should hold if they are not common. Okay. So so we are going to focus on this decision problem, and we're going to use this Bayesian decision theoretic approach. Essentially, on any given instance, we assume we have our rational agent doing the optimal thing. So we'll call YH here 0, YAI 1. This will come back in a later slide, not important now. But essentially, they're going to process the signal. They're going to form posterior beliefs, decide whether to go with the AI or the human based on utility maximization. And here the signal that we assume this rational agent is seeing is X, whatever our representation of the features is, plus YH and YAI. So it could be that the human did not see exactly X, but we have to for the purposes of evaluating decision making, we have to decide some X. So this might be what the AI saw, but perhaps we don't know for sure whether it's common with the human. Yes.
Is it possible to have a setting where it's like the human makes an initial decision, then they get to see what the AI would have recommended, and then the human can go back and revise their initial decision?
So we're not gonna, I'm not gonna take into account revisions necessarily, but yeah, you could implement it that way. All I'm gonna assume is that we can elicit this human prediction, this independent human prediction if we need to.
Right, and so it's like, if we did that, would it change much in this setup? Like,
If we did what?
if we allowed people to revise their decisions after seeing the AI decision, would that change much in this setup? Or like, is it mostly going to go through the same?
Yeah, I don't think it would change too much. I guess we'd have to think about what to do with that because it's no longer an independent source of information. So yeah, I'd have to think about that actually to give you a better answer. For now we're just gonna assume, these are both independent predictions, yeah.
So is it that they make sequential decisions and get payoff feedback during, or do they make all the decisions and then you evaluate?
We're not gonna necessarily assume, we're assuming there is some utility function governing this decision task.
But presumably the human could learn something about when to rely on AI if they received feedback during a continuous stream of decisions rather than making all the decisions and then getting the feedback.
Yeah, we're not, so I'm not actually considering any feedback now. We're defining a decision problem, so like if we, were to go into a hospital where they deployed some AI model, we would care about like what is the actual decision problem that the hospital believes is important here, that the human is solving. So what's the utility function that governs the quality of this decision?
But hold on a second. Assuming a utility function inherently changes how you weight the evidence, correct? If somebody has a cut versus an aneurysm, you're going to triage them differently. So how does your model address that?
We're just assuming a single scoring rule.
Okay.
Sorry, I just want to
Sure.
make sure I understand.
Sure.
So it's the latter, that essentially they make all the decisions and then they receive the payoff. In a clinical setting, I might take the AI's advice and then my patient might die and then I might learn something about when I should or shouldn't take the AI's advice, about when the quality of the
Yes, so we're not assuming that they're getting feedback
So
on
they
this.
make all
AI.
their
They use the
decisions.
umbrella.
and then they get the
So
Yes.
there's no learning.
There's
What
no
you're
learning,
What
no.
you're learning actually is the accuracy of the prediction. Because from one
Correct.
observation, you don't know whether you really
Correct,
shouldn't
but-
follow or not.
But the example given on reliance indicates that there is some structure to when the AI is right and wrong, because it's not just the rate, it's also when do I, for good reason, rely on the AI?
Yeah, which
and
is
when
all
do I, for
defined
bad
by
reason?
this joint distribution
Right.
or information structure. So we are assuming we have that, or we're willing to assert one, some joint distribution. So, so let's see, where was I? So yeah, our benchmark is the expected score of the rational agent choosing the utility maximizing action under the Bayesian posterior. For this decision problem, our baseline is their score choosing the best fixed action. The value of complementation is the difference between these. And so how do we use this value of complementation? Well, one thing we can do is, say we are considering deploying an AI in practice. So we have the ability to, take some labeled set of instances and apply our AI. We have the ability perhaps to elicit these independent human predictions, but we haven't deployed the AI, so we have not observed the human AI decisions. What we would like to do or know is that first that there is possibility for complementarity here. So what we want to see is this value of complementation should be large relative to the expected score of the baseline. If not, what that means essentially is that we're not getting much boost in performance when we're putting these agents together versus just going with whichever one is better in isolation. And so sort of the intuition here is just that pairing humans with AIs makes things a lot more complex. And so we would like to know that there's actually room for a boost. And this applies if you're a researcher designing studies, trying to study AI assisted decision making. Like, you want to make sure you're studying situations where this is actually a good idea, but it also would apply if you're doing this in practice and trying to decide, should I deploy an AI here? All right, we applied this to do sort of design analysis of existing studies in the literature on human AI decision making. This was a study by Lai and Tan on detecting deceptive reviews. So it was a human, they had AI decision support, and they were, deciding whether online product reviews were deceptive. And you can see here that when we compute this benchmark and we look at the baseline relative to it, there's very little room for, adding the human to do much at all. And so, there's less than sort of a 10% boost. And so, this makes us question, is this really a good setting for studying human AI decision making? Like, in reality, probably, we should just label with the AI whether these are deceptive or not, rather than, giving the human this choice. Other studies are a little bit better when we look at them just based on this design analysis measure. So here's one by Bonsall et al. There were a few tasks they studied. This is an LSAT task where people are doing multiple choice LSAT questions with AI decision support. And here we can see that the difference between the baseline and the benchmark is much larger. There's a lot of room to actually see something interesting by bringing in the humans. Okay, so that's, we can do that before we even deploy an AI to check that there's actual reason to bring these agents together. After we deploy an AI, now we have these AI and human predictions. We also have the human AI decisions. And this is where we can begin to try to understand, why did this human with the AI not do as well as they might have? So, we observe the human AI performance. We can see how far that is from our benchmark. And we can think about sources of loss here. One source of loss, if we think about sort of relative to this rational utility maximizing an agent, is that our human might be relying overall at the wrong rate. So our benchmark will tell us what the optimal reliance on the AI is. And so, the human may not be achieving this reliance rate. On the other hand, another type of error might be not that they're over or under relying, but that they're not relying in the cases where it is most in their best interest. So where the boost in going with the AI versus the human is largest. So the rational agent, is going to rely at the optimal rate, and they're going to rely on the instances where it's sort of going to give them the biggest boost, whereas the human might not. The way we're going to distinguish these is by creating another benchmark we're going to call the misreliant rational agent benchmark. This is going to tell us the expected score of the rational agent on this decision problem if we constrain them to rely at the same rate that we saw the behavioral agents relying. And so essentially, this rational agent, they're forced to rely at a certain rate that might be non-optimal, but they're going to always rely in the cases where it's most in their best interest. If you imagine sort of sorting the individual instances by the difference in expected payoff from AI versus human, they're going to take the top of that list. And so any remaining gap here between the benchmark is going to capture the loss simply from not relying at the right rate. What remains between the human AI performance that we observe and the misreliant benchmark then explains the loss in performance because the humans were not able to distinguish at the instance level when it was sort of in their best interest or most in their best interest to rely. And so, the point here is not necessarily that we can intervene on just one of these and keep the other fixed. These things, if we actually tried to intervene, would change together. But the idea is that when we see that humans are not performing as well as they could, we need some ideas about what might be going wrong. And the way we might try to address the problem, if the fact is that they're over or under relying in general, might be a different set of strategies or interventions than if we think that they can't really distinguish at an instance level, how their own probability of being correct is related to the AI.
Back to the behavioral economic stuff. So just to be clear, is the default that they get exposed to the AI rational agent, or do they have to ask?
They don't know. They're not seeing the rational agent at all. The rational agent is a type of intervention we could bring in if we have a good model of how humans do this task independently and we have our AI. We could give them decision support to try to close this gap.
That's what I'm trying to get. Is
Yeah,
the
we're
decisions,
not.
so there's no
We're just
persistent.
we're just trying to look at this problem or this question people ask, what is appropriate reliance? and define it in a sort of statistically coherent way.
But appropriate reliance may be different if they have to ask versus it's persistent or always present in their decision process or prediction process.
What do you mean? If they have to ask for the AI prediction, or
Yes, if I'm a
we're
doctor,
assuming it's always going to be like once we deploy the AI, it is always going to be.
it's always there. Okay,
Yeah.
that's what I wanted to.
Yeah, yeah.
I just want to clarify, so when you say optimal reliance, or does that mean, or the benchmark on the right, does it mean just 100% accuracy, or it's different?
No, it's optimal reliance is going to be defined by the rational agent who is not necessarily, like they don't have perfect information. They have the information available at the time of the decision. This is the best you could do on that decision problem given what was actually available at that time. So yeah, we're definitely not assuming 100% accuracy, and accuracy does not have to be our scoring rule. It could be any scoring rule we choose. Yeah.
So on the ability to recognize the right situations to rely or not rely, is this something that can be predicted a priori, or is it something you're looking for? What would predict the right situations to rely or not rely, or is this kind of only recognized ex post after we know this?
Right now we're talking ex post, but potentially the reason for doing, all of this, like trying to get at different sources of error, is so that we can drive interventions of various kinds. So, I mean, that opens a whole nother can of worms because now we're actually trying to change things. But yeah, the idea is that, we see these results. First, we want to know just what is the attainable performance, which is often unknown when people do this. And then we want to try to understand like what might be the bigger source of loss, and then, we might have different ideas. If the overall reliance rate is just too low or too high, then perhaps, we just need to make them trust the AI less or more overall. Whereas if it's, if they're really doing badly at the instance level, figuring out when to rely, it might be a different intervention. And the rational agent, showing them sort of rational agent based, predictions could be one intervention, but we are not doing that here.
Because sometimes it may just not be possible to recognize the right instances
Yes.
if they are undistinguishable on
Right,
all the
yes,
dimensions.
but that is the kind of thing this sort of approach should let us at least make a guess on. So yeah. Okay, we can apply this same sort of post hoc after we've deployed the AI analysis to existing studies. Here's this one by Bonsall et al. Again, where now we see the human AI performance in orange. We see there is a long way to go still to this rational benchmark. And when we compute the misreliant rational benchmark, we see that here this reliance loss is actually pretty small. It's more that people don't know when is the best instances to rely. So overall, they're relying at roughly the right rate. And so this gives us a little more insight relative to sort of the original analysis, which said this is a problem of reliance. So we have sort of a better sense of, there's reliance, difference from optimal, and then there's this other sort of issues. Okay, that's all I'm going to say about that. That's sort of a first demo of how we can answer this sort of evaluation question about reliance. What I now want to talk about or focus on a little more are these questions that involve explanations that might be part of a signal that we provide to a human decision maker. So, previously our model just assumed there's some X, which is in our information structure, and then there's these, two predictions. But in reality, often we believe we have to give the human more than just the AI prediction. We have to somehow give some explanation. Many explanations take the form like this, where the explanation technique is essentially a function of the features and the AI prediction. So I'm going to assume we have those types of explanations here. And often these will produce something like an instance level sort of feature importance map. So for this particular instance, here's the importance of different features in driving this AI's prediction. I'm also going to assume here that our AI model is essentially fit to the same distribution as our information structure that we're evaluating the decision problem on. So I'll just note that here. So yeah, this is the form of our explanation. And so explainable AI has been a topic for research now for about 10 years. And there are many different explanation techniques of the form that I just showed. And there's also a lot of back and forth or debate when it comes to what properties make an explanation valuable. So there's a lot of demonstrations or arguments about, for instance, fidelity of the explanation to the actual information that the AI prediction was using. But there's also more human-centered proposals, things like, explanations ultimately are only valuable to the extent that they are actionable, meaning they should somehow help a human decide what to do next. However, there's a lack of theoretical foundation or common sort of consensus way of thinking about what an explanation even is, that then leads to sort of a lack of clear definitions for some of these things. So actionability is sort of, gestured at, but we don't really know how to define that. When we consider what makes an explanation valuable from this decision theoretic view, we'll get a clearer definition of the value of an explanation. So, an explanation is valuable to the extent that it improves the expected performance on that decision problem when we offer access to that explanation. So, if we want to get a sense of the theoretic potential for some explanation to help a decision maker, we could ask questions about, as we change the information structure to say include an explanation versus not include one, how does that expected value of the signal to the rational agent change? So recall that our information structure is just going to be a joint distribution over the signal and the state. Here I'm going to say the signal is V just because it might include the features of the instance, but it might also include, other elements like explanations and AI predictions. And so, we might, first think about, well, we could try to quantify the value of the signal, including sort of the full information we might expect to give the human, the features, the AI prediction.
What is the definition of an explanation?
An explanation is just going to be an element of a signal that we're offering. It's just a signal. So an explanation,
No, it's not just a signal.
So
It's
it is a
signal with a
function
certain
of-
purpose. The purpose of the signal is what?
The decision maker has access to some signal, they make a decision. So the signal is the information that they have access to.
How is that an explanation?
The explanation, so we are assuming that there are some features, there is some AI prediction, which is a function of the features and the state, and there is some explanation, which is a function of the features and the AI prediction. So those are the assumptions.
But we all know that correlation is not causality, correct? So the explanation can just be a made-up correlative thing, which is, some people might say a rationalization. Okay, that's
It could
fine.
be any function of the features and the AI.
So the explanation, as you've defined it, has no
Yeah.
relationship to truth.
It is
Okay,
a
that's
function
fine.
of the features and the AI
Yeah,
prediction,
that's
yeah. So yeah, we could start by quantifying the value of this signal to the rational agent. So going from the prior to having access suddenly to this full signal. And we might think, given what we believe about explanations helping humans, if we were to then calculate the value of a signal that removes the explanation from this component on the right, maybe it would be somewhere in here, right? Like the explanation should boost expected performance. However, with a rational agent, the explanation, if we take it away from the signal, the rational agent is going to do just as well as they would with the explanation. Because again, we're talking about this common type of explanation, which is just a function of the features and the AI prediction. And what this means is that, the explanation is just a garbling of the features. Similarly, if our AI model is fit to the same distribution that we're evaluating on, then the AI prediction is also just a garbling of the features in an economic sense. And so, essentially the rational agent with the features is going to give us this upper bound. So this is different from how we think about explanations for humans, because for humans, we assume that this explanation can actually help them. And so what does this sort of mean, about assumptions we bring to explanations? Well, I think, one way to interpret this is that we assume that humans are, not the ideal decision maker. So the humans either are less informed than this, Bayesian rational agent who has access to the joint distribution, or they might have access to that information, but they're bad optimizers. And so, an interpretation of this, if we think about how humans are different, is that somehow the explanation is going to help the humans unlock information in the features in a way that the rational agent simply doesn't need. So we might think, well, how does this rational agent benchmark with X help us given this difference between these two types of agents? Well, one thing that it tells us then is that, sort of the best case, if our humans are no more informed about the information structure, is going to be this rational agent with just X. So, we should essentially be able if we're going to study explanations, to find some decision problems where we can show that there is some potential theoretic value of the explanation, meaning that the features actually would boost performance on the problem. So if the explanation helps people get more information from the features, that's actually useful to this problem.
Just a clarifying question. So far we've been operating under like this statistical decision theory framework where we assume that even our like human agent is like doing some kind of optimization, right? So what does it mean that like they're not optimizing correctly, like human?
We're not assuming our humans are doing something optimal. We're comparing them to a benchmark based on, you know, this normative.
I see. And I guess you're going to talk about.
We're not assuming anything really about them.
Got it. And you're going to clarify what you mean by like unlocking info in X or Y.
Yeah. So I think that should be clear already. So that we're talking about, you know, how essentially to a rational agent, once you know X, you don't get any additional information from an AI prediction fit on that same distribution, and you don't get any additional information from an explanation, which is just a function of the AI prediction in X. So X contains all the available sort of decision relevant information. We could look at this benchmark with the rational agent with just X as sort of telling us, you know, for humans that don't have access to additional features over what we know of, this should be an upper bound essentially. So it's different from our intuition because we think explanations should be part of this, but they don't need to be in this framework. Yeah.
So you're assuming that the theoretical value of explanations is always positive.
As long as the going from the prior to access to the features actually improves decision performance, yes. So I'm assuming it is always going to be, yeah.
So there's no case in which the function E of X and prediction actually makes it harder for the human to map
It could totally make it harder for the human. I'm never making assumptions about human when I sort of set up my benchmarks. So here what I'm saying, the assertion I'm making is that if the human does not have additional information over the information structure, then this will be an upper bound on how well any human could do with an explanation. If we believe the human might have access to additional information, I'm just going through my slides now, then we might see that if we were to create the benchmark taking X and the human predictions, that could be higher. So essentially, you know, we often don't know going into these human AI decision support cases, like what features do humans actually have access to? We know we can define sort of a distribution on which we're evaluating. We often know the distribution our AI model is trained on, and we're trying to construct sort of benchmarks representing best attainable decision performance, but exactly what the human has access to, we don't know. And so, you know, if they don't have access to more than this data generating model, then this benchmark, the rational agent with X, will upper bound their performance. One way we can check whether that's the case is try constructing the benchmark where now we offer the rational agent also these independent human decisions. So if there is additional information that is decision relevant in these human predictions, we'll see a higher value. Yes?
So just going back to the definition of an explanation again, so you said it's a function of the features X and then this is like Y AI.
Yeah, so things like Lime, SHAP, a lot of these common ones take that form.
In this framework, like you said, the rational agents, if they knew Y AI and X, like adding the explanation on top of that is sort of like doesn't give any extra information.
No, it's just a garbling from that.
Yeah, so I was just wondering, like intuitively it seems to me that like in many settings, maybe providing an explanation is also like it might reveal some additional information, like the AI has some reasoning process, and like there's actually many different reasoning processes which like could have led to like the given Y AI. So like maybe knowing X and Y AI is not sufficient information.
Yeah, so
I'm just wondering how that fits.
given the assumptions I'm making, the explanation is never going to help the rational agent over X. However, you know, we often, you know, with humans, we expect the explanation to help. One thing we could do, which will not give us any kind of upper bound, is look just at the value of information of the explanation alone to a rational agent. So that could give us a sense of sort of like which explanations kind of correlate more with the state.
I just want to be clear though, if you're explicitly citing Lime and SHAP, those are not explanations, those are assignations of attribution. That's it.
Yeah.
Attribution and explanation are not the same thing.
So how do you define explanation?
You're the one presenting it. That's why I keep asking you to define
Yeah, I'm
explanation.
defining it as in this case,
Attribution and explanation are interchangeable.
yeah,
That's
as
fine.
I just defined
Okay.
it,
Okay.
it's a function applied to X and, yeah, the AI prediction.
Okay.
So I would say that's the most common form I see. Yeah, but obviously there's many ways to explain things. But when we're talking about explainable AI, that is what the form that many are going to take.
So I just wonder if I could follow up on this. Like,
Sure.
It seems to me like it's a little bit different to me if like an AI said, hey, I took these features and then I just ran a random number generator and then outputted this Y AI versus I took these features, went through some like very deep reasoning process and then arrived at this.
Yeah,
Like
from
AI,
our perspective, all we care about is the decision relevant information. So the correlation of that signal with the ground truth state. So we're not going to be able to, like, the rational agent is not going to see a difference, essentially, as long as the ultimate, information value is the same. Like that's what I'm saying. Like if we want to test sort of like how well does the explanation itself correlate with the state, like how much information does it give us about the state, then we could compute this value of information where the rational agent benchmark is the rational agent just with the explanation, not the features. So that would give us a read on like how much information about the state is in this explanation technique, but it's, ultimately we're just looking at this from sort of statistical standpoint, like how much information is encoded in this signal.
Right. And just one other question, like, do you assume that AI has like sources of information which a human doesn't have?
That could be the case. It could be that the X available to the AI is, like the human X is a subset of that, but it could also be that the human has just access to different features or more features. So we don't want to make any assumptions going in about what information the human has relative to the AI. We are assuming that the AI has the X that, we're evaluating over.
I'm just like picturing a scenario where like, for instance, the AI sees X and it also has some sort of like additional independent information not observed by the human, and it combines those to produce like Y AI, but like Y AI alone is not a sufficient statistic for recovering the information of the AI, so like we might want the explanation as a way
We
to-
should probably talk
Yeah,
offline. Can you tell me later? Yeah, because I think I'm running out of time. So yeah, like I said, we can try to check where we are in terms of the human's knowledge. Like, could it exceed this information structure we're using by looking at the rational agent benchmark now giving YH as well? And we can look at the complementary value of information before we even deploy our AI and explanation by looking now at what is the boost in expected performance in the best case of the rational agent when we go from just having the information in the human predictions to having the information in the human predictions plus X. And so essentially, what we're assuming here is that any information that the humans have access to will be revealed by variation in their predictions, YH. And so we would want to know before we deploy a prediction, an explanation that, that this function of the explanation in unlocking additional information in X is actually useful. Like if X doesn't have much additional marginal value over the information the humans already have, then the explanation is probably not going to help us much. Okay, so these are both sort of these last two, this theoretic value of explanation and complementary value are things we can compute before we actually deploy the AI to assist the human with this explanation technique. Of course, after we deploy the AI with the explanation, often we care about estimating the treatment effect of the explanation. So, typically our sort of best case is we run a controlled experiment where we randomly assign the signal with the explanation to some people and the signal without it. In the other condition, and so we can estimate this behavioral value of explanation. And so what we want to do then is interpret that in the context of these theoretic values. So we're sort of, in this kind of framework, again, the decision theoretic framework, we're trying to get a sense of like, if we see humans doing this much better with an explanation, how does that compare to sort of the full information value that this explanation could have unlocked for them? So yeah, this is sort of work that was just done recently, so I'm still sort of figuring out all the applications, but I would say the overall idea of this is that, when people come up with new explanation techniques in sort of the ML research literature, how to validate those is often unclear. Like, how do we know what an explanation should actually do? And so, what I'm arguing is that first, when we come up with an explanation technique, we should be able to identify some class of decision problems where we can show that, there's potential theoretic value. So being able to unlock information in the features actually makes a difference on this decision problem. Then we should be able to show that, given what we know about human judgments in this domain, the explanation also could offer additional information there. And finally, we can estimate the treatment effect in the classical way, and we can interpret it within this framework. So trying to sort of provide a more rigorous theoretical foundation for explainable AI research. All right, I think I'm running out of time, so I end at 12, right?
Yeah.
Okay, so I will just skip to the end. I was going to talk about some cool things we could do going further with this complementary information notion, where we want to sort of identify, given some agent decisions, how much additional value is in some signal. But I don't have time to go over that in detail, so I will just refer you to my paper. Yeah, I'll just wrap up. Here we actually come up with a new explanation technique. But yeah, I think, the sort of point of the work that we're doing applying statistical decision theory to these human AI problems is really that first, when we're trying to understand decision support for humans, we have to identify specific decision problems that we are targeting and understand sort of what behavior is possible in those problems. And if we can calculate the value of signals, this ends up being sort of a very robust way to get insight into, what's possible for that decision problem in terms of information use. We can look at things like, what's the best case of combining the human and the AI intelligence? What's sort of the best an explanation could do here? And I didn't get into it, but we can also look at sort of which features does the human appear to be relying on versus an AI. So, all right, thank you for the great questions.
Quick question. You mentioned somewhere along the way about the cognitive, you didn't say cognitive, but you said the complexity of human and AI combination. Yeah. But I didn't see any theoretical sort of...
No, I'm just assuming there, so...
There's no cost here.
I'm not modeling cost,
yeah.
No. I mean, I think that's a next step for a lot of this, but is that we assume as soon as we provide some extra information signal like an AI prediction to a human, that is a big cost. I do think something I didn't mention, like in terms of caring so much about is there room for complementarity, I do think there's situations where people are deploying AI models where you could see that there's no real room for added boost by bringing in the human. However, the human has to be the final decision maker. So there's still settings like medicine, et cetera, where we're not willing to just bring in an AI. And so, what we're trying to do is in many ways give people a tool to tell, like when there is some choice, do we actually want to bother bringing in this AI with the human, or should we somehow be applying the AI offline and then just, trying to take this aspect of decision out?
Very cool.
Thank you.
Thanks, everyone. There should be cookies left. Take some so that I don't take them all home. Our next seminar will be on November 13th with David Rothschild for Microsoft Research.
All right.